Well, howdy folks. We're working on this pre-work, which is looking at the graphs of the trig functions tangent and secant. And on the first page, what I had you do was kind of review the connection between the unit circle and then the graphs between the functions when graphed on the traditional xy axes. And what's always a little bit confusing is separating our knowledge of the unit circle, getting information from it, but recognizing that the roles of theta and x and y may play different entities over here than they do when we're over here discussing this function as a traditional function. So you should have resketched the graph of the sine function on your own. And then what I'd like to do here is let's go ahead and construct the graph of the tangent function. So we'll work through a few of the important details of the tangent function. The function f of x equals tangent of x. It inputs numbers from, you would like to say that from the real number line, but the problem is because, in fact, let's go ahead and jump to it. It outputs the ratio of the opposite side over the adjacent side of a right triangle when formed in standard position. And if we go look at on the unit circle here, if we think about the tangent value for any given angle theta, the tangent value is the ratio of y over x. And because of that, you'll notice that we're doing division, and unlike a sine and cosine, where the denominator was the hypotenuse, and the hypotenuse always on the unit circle is just that radial arm, which is always 1, or just r if we're using just a standard xy point. Here, we could have an x-coordinate of 0, and so we need to exclude whichever angles make the x-coordinate 0. And so the domain of the tangent function is the set of numbers. Here I'm thinking of x as my input, so it's a set of numbers x such that x is any real number, just like we've said before, except that x cannot equal 2n plus 1 pi over 2 for n an integer. And I'm sorry, folks, there's just never enough room to fit that on there for n an integer. So let's talk about that in just a second, because you should be feeling a little bit overwhelmed by this expression right here. Well, if we go look at the expression tangent of theta equals y over x, we see that when theta is the angle, say, pi over 2, the corresponding ordered pair there would be the ordered pair 0, 1. Likewise, when theta is, say, 3 pi over 2, the ordered pair would be 0, negative 1. So notice that if I try to compute the tangent of pi over 2, if I do this naively, what I'd be trying to do is I'd be trying to set up the ratio of 1 over 0, and that's undefined. So this is undefined. And so what we see is that the tangent expression is undefined for multiples, and I should be a little careful here, odd multiples of pi over 2. So notice it's undefined for 1 pi over 2. It is defined for 2 pi over 2, but not 3 pi over 2. It is defined for 4 pi over 2, which is 2 pi, which would land me right here. But it's not defined again when I get up here as a second lap around at the angle 5 pi over 2, nor 7 pi over 2, nor any of the odd multiples of pi over 2. So the only thing then to say here is that this is just saying we're not going to allow x to equal an odd multiple of pi over 2. Why 2n plus 1? Well, if I take a number, any number n, and I double it, that number is now even. And if I add 1 to an even number, I'm guaranteed to have an odd number. And so that's where we come up with that 2n pi divided by 2, because I only want the odd multiples of pi over 2. Notice if n is 0, for instance, I would just have 2 times 0, which is 0 plus 1, or I have 1 pi over 2, which is just that 90 degrees right here where the tangent is undefined. And as n takes on different numbers, we get different odd multiples of pi over 2. Okay. So we'll talk more about this domain in a second, but let's go ahead and state it one more time just for practice. It's the set of numbers x such that x can be any real number except that x does not equal an odd multiple of pi over 2. So pause the video, practice writing out an odd multiple of pi over 2. And we have to add here, because n cannot be any real number. It can't be, say, the fraction 1/2, or it can't be the square root of 2. We have to add here that n must be an integer. And just as a reminder, the integers are the numbers. They're all of the counting numbers, 1, 2, 3, yada, along with 0, and along with each of their opposites. So those are the integers. There should be dot, dot, dot in front of that, folks. Those are the integers, and we're saying that if I pick an integer and then develop an odd multiple of pi over 2 that way, we're not allowed to let x be that value. That angle is forbidden in our calculation for tangent. Okay? The range of tangent, interestingly enough, is minus infinity to infinity. And we see that if we think about this, the formulation of the tangent of theta equaling the opposite side of that reference triangle over the adjacent side, because the adjacent side of a right triangle can, even on the unit circle, that side right there could go to having a length near 0. This expression can blow up in either the positive or negative direction, depending on the sign on the coordinate associated with that right triangle. Okay. So we've got that the domain of the tangent function is all real numbers x except for the odd multiples of pi over 2, and that'll be important when we look at this graph. And then the range is from minus infinity to infinity. If you have questions about that, folks, I'm not looking for mastery in this video. I'm just trying to do some of the groundwork. So please, if you have questions, ask me about this during class or come by and see me during office hours, because I'd like to give you a better explanation for that, but that might be best done on a one-on-one interaction. So just as a reminder that we measure the angle as x when we're using this formulation, f of x equals tangent of x. X is taking the role of an angle right here, and that is of course confusing because when we first defined tangent as a ratio of an angle theta for an angle in standard position, we said it was y over x. So what's difficult here is this x here, which is playing the role of the length of the adjacent side of this triangle right here, or the x coordinate of any point on the unit circle. That x is not the same as this x right here, which is playing the role of theta, and that is definitely a confusing fact of life. Next thing I want to say about tangent is that the tangent function is not continuous on the entire real number line. We're not going to define what that means in this class just yet, and we'll just give an overview later on. But roughly speaking, we can say that we are not able to graph the graph of tangent of x without picking up our pencil. And more specifically, we'll say that the graph of tangent of x has vertical asymptotes everywhere it's undefined. So let's go down and start looking at the graph of the tangent function. We want to start constructing this graph here. And so we just said that the tangent function is not going to be defined at all of the odd multiples of pi over 2. Well, look, here's an odd multiple of pi over 2. Here's an odd multiple of pi over 2. I didn't write it, but this would be 1 pi over 2, 2 pi over 2. This would be 3 pi over 2. Here would be another odd multiple of pi over 2. It would be 5 pi over 2. There's minus pi over 2. So the tangent function will not be defined at any of those tick marks that I just constructed there. Well, in fact, we said that the function, the graph, is not continuous, meaning when I go to sketch the graph of tangent of x, I'm going to have to pick up my pencil when I sketch it. And we said that the tangent of x has vertical asymptotes everywhere it's undefined. Now, why is that? You'll get a better explanation of that when you get to your calculus classes, but for right now, I'm just asking you to accept that this has vertical asymptotes at all of the odd multiples of pi over 2. So I'm coming onto the graph, and I'm sketching all of those vertical asymptotes, one at each odd multiple of pi over 2. Okay. If these graphs weren't labeled, I would label these. Here we have the vertical asymptote at x equals pi over 2. Here we have the vertical asymptote at x equals 3 pi over 2. In general, I ask if you sketch several vertical asymptotes when you're graphing a trig function to label a couple of them. Okay. Let's put a pin in this calculation here. We'll refer back to this odd statement here in just a second. Let's go ahead and plot a few points on my tangent function. So if I ask you for the tangent of 0, when x is 0 on my x-axis, what's the tangent value going to be? Well, if we go look at the unit circle at the angle 0 degrees, is a little silly here, but at the angle 0 degrees, we have the ordered pair 1 comma 0, and tangent is the ratio of 0 over 1, and so the tangent of 0 is just 0. So I can go plot that ordered pair right there. There's the ordered pair 0 comma and then the 0 that was outputted when I computed the tangent. Okay. Likewise, we could find the tangent of, say, pi over 6. The tangent of pi over 6, to determine that, we go to the angle pi over 6 and we label that ordered pair on the unit circle. Make sure you can see that, folks. You go label that ordered pair on the unit circle, and that would be the ordered pair the square root of 3 over 2 comma 1/2. And when I want the tangent, I take the ratio of the y coordinate over the x coordinate, so that's 1/2 divided by the square root of 3 over 2. That reduces down to 1 over the square root of 3, and I'm actually fine with you leaving it that way. 1 over the square root of 3, we could get a decimal approximation for that. And so just so you know, that's approximately decimal 0.58. So I can now go to the x coordinate of pi over 6, and if I go up to about 0.58, and you can see I've actually made tick marks for you to help reference pieces. So there's the tick mark 0.58, and so that would be the ordered pair. This is going to get a little cluttered here, but that would be the ordered pair pi over 6 comma the square root of 3, 1 over the square root of 3. Okay. And I want to put that in blue so it matches that. So 1 over the square root of 3. Likewise, if I went and computed the tangent of pi over 4, that is equal to, if we go to the angle in standard position, there it is in standard position there. If we go to the angle pi over 4, that has the coordinates root 2 over 2 comma root 2 over 2. It goes out the same, it goes up the same. So I'll just say that's root 2 over 2 divided by root 2 over 2. That's the, careful, that's the y coordinate over the x coordinate, but that's going to reduce down to just 1. So at the ordered pair pi over 4, we're going to go up to the x coordinate 1, or excuse me, the y coordinate 1, and so we'd have this ordered pair right here, which is the ordered pair pi over 4, comma 1. And hopefully you're starting to see the method here. I'll just cut to the chase. If we do the tangent of pi over 3, that's going to give us just the square root of 3. And giving a decimal approximation of the square root of 3, that's approximately 1.73. And so if I go up to where x is the pi over 3, we'll go up to square root of 3 on this axis here. That was square root of 3, that was 1 over the square root of 3. And so we'd go up to this point on the axis right here, and now I can begin filling in the graph of this function. What we see is that as my x coordinates approach this value right here, pi over 2, this odd multiple of pi over 2, as my x coordinates approach it coming from the left, the y coordinates are just going to keep getting larger and larger. And that fits when we said that the range of this was from minus infinity all the way up to infinity. And if we were to sketch the going in the opposite direction, if we were to go minus pi over 6, we'd be here. And if we go to minus pi over 4, we'd be here. And here we'd have the remainder of the graph of the tangent function. Let me zoom down a little bit. I think I can sketch that a little better. Let's try that one more time. This would be this ordered pair right here, and we can continue graphing the tangent function. Now that was just one period of the tangent function sitting inside here. Now I want to point something out. Notice that when I plugged in, say, pi over 4, I got out 1. The tangent function is what we called an odd function. When I plug in minus pi over 4 into it, it's an odd function, so I get out the opposite value. When I plugged in pi over 4, I got out 1. When I plug in pi over 4's opposite, I get out the opposite value. That's because the tangent function is an odd function. Okay? So let's finish sketching the graph of the tangent. There's lots of ways to draw this. You could plot more points if you wanted to, but basically we have that it's a periodic function, and we begin to make several periods of this shape. My recommendation, just as a practical application for trying to sketch the graph of the tangent, is to go to plot your asymptotes here, like I just did. In between, at pi, by the way, the tangent of pi, it is in fact 0. You could verify that. And same with the tangent of 2 pi. But the tangent of pi is 0. And then I'm going to draw this generic shape here to show the behavior as we approach 3 pi over 2. And I'll draw this generic shape here to show the behavior as I approach minus 3 pi over 2. So I sometimes have students, and they're more dexterous than I, and they're able to draw a nice sketch of this squiggle sort of shape all the way through in one fell swoop. But for me, I find it better to plot in the middle, sketch one side of it, and then come along and sketch the other side of it. And we can finish out the graph of this tangent function. Okay. And here we see that the tangent is a periodic function. Okay, so let's go ahead and say that. It's periodic, but it's what sort of periodic? The sine and cosine functions were 2 pi periodic, meaning they didn't repeat themselves until we got back to 2 pi. Every 2 pi they repeated themselves. And the tangent function actually has a period of just between the two asymptotes, and so it is pi periodic. You can see that, for example, here if I'm at 0, if I step pi units away, I'm at the exact same spot. Or if here I'm at pi over 4 comma 1, if I step exactly pi units away, meaning the distance between those x coordinates is pi, I'm back to the same point on the graph. So that's what we mean when we say that the function tangent of x is pi periodic, meaning that if we were to take the tangent of x, that's the same thing as the tangent of 2 pi. Oops, excuse me, that's true, but it's pi periodic. That's what I want to emphasize. So pi plus x, okay? Meaning the graph of tangent of x repeats itself every pi units. The last thing I wanted to mention here is that the tangent of x is an odd function, meaning that when you plug in negative x, you get out the opposite sign of what you got when you plugged in x. That's a little bit clunky. I feel like math people love this definition for the definition of an odd function. It's great, but another way to say that is that opposite domain values have the opposite range values. For example, when you take the tangent of pi over 6, we saw that we got square root of 3 over 3. By the way, that's the same thing as 1 over the square root of 3. It's just that I've rationalized it here. When you take the tangent of pi over 6, you get out square root of 3 over 3. So if you plug in the opposite of pi over 6, I'm plugging in minus pi over 6, I'm going to get out the opposite value there. That's because tangent function is an odd function. And just as a quick reminder, folks, some functions are even, some are odd, and a lot of functions are neither even nor odd, but our tangent function is an odd function. And you can see that in the symmetry in this graph when you reflect about the origin. Folks, that's a long video. I appreciate your patience as we went through this graph. I'll do the next one quite a bit faster when we look at the graph of the secant, but hopefully this gave you some insight into how we sketch the graph of the tangent function. Thank you for your patience. We'll see you next time.